I'll be going over the end behavior of polynomials. We are going to use the simple polynomials representatives: y equals s squared, y equals s cubed, y equals negative s squared, y equals negative s cubed. That's cubed right there. Okay, so, well, this is the graph of y equals s squared is very easy to memorize. So I will encourage you to just know that the graph of y equals s squared is just a basic parabola. So with two branches, or both pointing up like that. Now, when you have a negative in the front, it's called a negative leading coefficient. Here is positive leading coefficient because there's no negative in the front, so it's not reflected. This is a reflected graph with a negative leading coefficient. So the graph will look like this. It will look a reflection across the x-axis. All right, so these two graphs, you just need to know them. Here is the other one, y equals s cubed, is the representative odd degree polynomial. This one is a representative even degree polynomial because the exponent here is even the even number. The highest exponent is 2, is even number. Here the highest exponent is 3, is the odd number. So basically, the graph of s cubed look like this, and I will encourage you to memorize it. This is how it looks like. So it goes straight up like that, and the other branch comes straight down. So if you reflect this across the x-axis, it will look like this. This is going to go up there, and the other one is going to come down here. So basically, if you memorize these shapes of all these four graphs, you'll be able to determine the end behavior of any polynomial at all, because they represent any polynomial can either be even degreed or odd degree. So let's go ahead and write the end behavior. The end behavior really is just all about what happens to y as x becomes extremely large, increases beyond bounds. Okay, so when x becomes so large, as we plug in more x value and becoming very large, the y value begins to go very, very high as well. So you can see so I'm going to write this one for the right side. As x becomes extremely large, y becomes extremely large as well. Okay, that's it. That's the right side. Okay, compared to the left side, if we are plugging in negative numbers into this function over here, the value also goes very, very, very high. We are not going to get a negative number, because if you do a negative number squared is a positive number. So the number is going to, the y value is going to continue to grow very large towards positive infinity as well. So as x goes toward negative infinity, y also approaches infinity. Okay, so my infinity is not quite good, but that's good enough. All right, so the left side and the right side of this graph. Okay, let's go to this one. The left side and the right side of this graph. When the leading coefficient is positive, as s approaches infinity, y approaches infinity as well. You can see as we're going towards the right side, plugging in more positive value of x, the graph is going way up to infinity as well. On the left side, as we go toward negative infinity, the graph is growing on the opposite direction, going toward negative infinity. So as x approaches negative infinity, y approaches negative infinity as well. Okay, so that's for the positive leading coefficient type of functions. Now, if we go to the negative leading coefficient type of functions, So the right side, we can see as x approaches infinity, y approaches negative infinity. You can see it's growing towards the negative side, negative numbers. But as x approaches negative infinity, y approaches also negative infinity. Okay, so you can see it's pointing down, going towards negative infinity. All right, the right side of this. As x approaches infinity, you can see that the y is going down to negative infinity. So as x approaches infinity, y is approaching negative infinity. On the left side, as x approaches negative infinity, as x approaches negative infinity, we can see that y is approaching positive infinity. Y is approaching a positive infinity. So basically, that's a description of the end behavior. We can see in an example I want to show you now. Let's say I have a function that we don't have a graph of it, but we want to be able to describe it. Here's an example of that. So let's say I have a function like this. I have f of x